All right, let's peel back the cover on our digital world and look at something that's absolutely fundamental, but you probably never see it, the digital counter. Let's dive right in. So think about it for a second. Counting seems, well, simple. But how does a hunk of silicon actually do it? I mean, everything from the timer on your microwave to the most complex stuff happening inside your computer, it all comes down to this one basic ability, counting little electrical pulses. And believe me, this isn't some obscure high-level tech. These circuits are literally everywhere. They're in your kitchen timer, they're managing traffic in parking garages. They're kind of like the silent, tireless accountants of the entire electronic world. So what is this thing really? Well, the definition is surprisingly simple. A digital counter is just a circuit built to do one job: count the number of electronic ticks, or what we call clock pulses, that you send its way. Just picture a finger tapping once for every single electrical beat. That's it. Now, there are a couple of different ways you can build one of these counters. The first, and the simplest, has a kind of nerdy name. It's called an asynchronous counter, but everyone knows it by its nickname, the ripple counter. And honestly, that nickname is the perfect way to understand how it works. I want you to picture a long line of dominoes. You just nudge the first one, right? And it knocks over the second, which knocks over the third, and on it goes. A ripple counter works the exact same way. That main clock pulse only pushes the very first part of the circuit, and then the output from that one triggers the next one in a chain reaction. You can actually see that domino effect right here in the circuit diagram. See that clock signal, CLK? It only connects to the very first block. That block is called a flip-flop, which is basically just a simple memory circuit that acts like a light switch. It's either on or off. Then the output of that first switch, which is labeled Q, becomes the input that triggers the second one. That right there, that's the ripple in action. So, okay, let's actually walk through the count. The first pulse hits, and that first switch flips on. Our output is now 0001, which is binary for the number 1. Simple enough. But now watch this. With the second pulse, that first switch flips back to 0, and that very action is what triggers the second switch to flip on. Now our output is 0010, which is 2 in binary. You can see how this chain reaction just keeps building up the count with every pulse. And this timing diagram, it lays out the whole story perfectly. Each one of those horizontal lines is one of our binary bits. See how a change in that top line, QA, causes a slightly delayed change in the next line down, QB, and so on? Those little offsets, the ones the arrows are pointing to, they're not mistakes. That's the actual physical delay as that ripple effect travels down the line of dominoes. And that right there brings us to the biggest problem with this beautifully simple design. That tiny little delay, that small imperfection in our domino chain, it turns out to be a really critical flaw. The fancy technical term for this is propagation delay, and it's built right into the design. Because each switch has to wait for the one before it to finish its job, a delay starts to pile up along the chain. To put it bluntly, these ripple counters are just plain slow. So why does this even matter? I mean, who cares about a few nanoseconds? Well, when you have billions of things happening every single second inside a modern processor, those nanoseconds add up fast. The final domino can fall so late that by the time you actually need the final count, it's just wrong. The ripple has become way too slow for the modern digital world. So clearly, engineers needed a better way, a much, much faster way. They needed a solution where every single domino fell at the exact same time. They needed a synchronous counter. Okay, this table here just lays out the difference perfectly. On the left, you have the asynchronous or ripple counter, that chain reaction we talked about. But look at the right, synchronous. All the flip-flops get the clock signal at the exact same time. What does that get you? No propagation delay and much, much faster speeds. The only real trade-off is that, yeah, the design is a little more complicated. And the secret is right here in the circuit. Look at that clock line, CLK. Unlike the ripple counter, this one signal branches out and connects to every single flip-flop at the same time. And those extra little logic gates you see, they're the smarts of the operation. They let the circuit figure out ahead of time which switches are supposed to flip on the very next tick. It's just a much smarter, totally coordinated system. This is the guiding principle. Instead of a whisper being passed down a long line of people, this is like a commander shouting one order to the entire group simultaneously. Everybody who needs to change does it at the exact same moment. No waiting, no delay. So we have the slow but simple ripple counter and the fast but complex synchronous counter. Let's bring this all back from these diagrams to our actual lives. Where is this digital pulse really beating? Well, we're right back where we started. That digital clock on your wall, it's using a counter. The system that tells you how many spots are left in that downtown parking garage. Yep, that's a counter too. They truly are one of the most fundamental building blocks of this entire digital world we all live in. When you think about it, it's a pretty amazing story. We start with a simple idea, like a chain of dominoes, and we get a slow counter. But then, by making one key change, synchronizing that chain, we get something fast enough to power our entire world. It really makes you wonder, what other incredibly complex systems that we rely on every day are built on an idea as simple and fundamental as just counting?